Hi, and welcome to this presentation for the 2021 Georgia Water Resources Conference. My name is Scott Pippin. I'm a member of the Public Service faculty at the University of Georgia's Carl Vinson Institute of Government. And I'm here to talk a little bit about a project we recently wrapped up looking at the relationship between septic system vulnerability and sea level rise. This is a project that was funded by NOAA's Office of Coastal Management through their Coastal and Ocean Climate Applications Program. If you've tuned into this presentation, you're probably basically familiar with how a septic system operates, but just by way of background, in case you're not, a septic system really is two pieces of equipment. It consists of a septic tank that receives wastewater, generally from a residential structure. And in that tank, heavier solid materials generally settle to the bottom, and the liquid effluent, as it's called, flows out of the tank and into a drain field or leach field, where the water then percolates through some sort of medium into the soil, and through the soil it gets treated by microorganisms, various biological processes, as it moves down and eventually hits the groundwater, where it then flows in the general path of the groundwater and merges with the surface water, whether that be an estuary or bay or the ocean or other surface waters such as a lake, stream, or river. So in coastal environments, well, generally speaking, septic systems can function very well for a long period of time and provide adequate treatment for residential wastewater. However, in coastal systems, there are a number of environmental factors that make septic system functionality more challenging. The soils sometimes not suitable. Either they percolate too fast or not fast enough. Often there's a high or widely variable groundwater table that can make designing and installing the systems with enough separation to provide that treatment challenging. And also in coastal environments, the system may be more vulnerable to overland flooding, either from tidal flooding or storm surge or other events that can impede its functionality. And all of these problems are expected to become worse as sea levels rise. When we talk about sea level rise, we're generally focused on the overland impacts. How much higher are tide levels going to come? How much higher is the storm surge going to be because of climate change and because of sea level rise? However, as those tides rise and as that sea level rises, it leads to a corresponding impact to the groundwater table. Basically, the angle of incidence, as they say, between the groundwater and the surface water will increase, and that's going to increase the pressure on the groundwater table and push it closer to the surface. Now, in terms of septic systems, this, as I said, you need to maintain a certain level of separation between the bottom of the drain field so that there's enough distance for that water to percolate and be adequately treated before it reaches that groundwater table. Therefore, as that groundwater table rises, that separation will diminish, and that will lead to increased septic system contamination in the environment. This could either be direct through a complete mechanical failure of the system. If the groundwater table reaches the septic tank or reaches that leach field, it can cause a complete system failure, causing a direct discharge of septic system or of sewage into the groundwater, or cause a mechanical failure that causes that sewage to back up into the home or into the yard, where people could be directly exposed, which causes all sorts of really nasty public health impacts, and it's just generally pretty gross. Or it can just diminish the treatment that wastewater receives as it's leaving the drain field. This is a much less dramatic, much less noticeable impact. And so it's anticipated a lot of system experiences, and that just will lead to higher levels of bacteria and higher levels of waste entering the environment. And of course, there are systems that are more resiliently designed or well located that will be able to accommodate some level of sea level rise and higher groundwater tables for some time to come. So the focus of this project is to begin an effort to really understand how higher groundwater tables and how sea level rise is going to impact systems in these different ways, and thereby help communities and help regulators understand what that means for future land use planning and future wastewater infrastructure planning and how they're going to be able to accommodate both the existing development in coastal environments where these things are going to be more challenging, and how they're going to plan for future development and what type of housing and wastewater infrastructure is going to be adequate under these increasingly difficult situations. So as a foundational element of this project, it really comes from a lot of work that was done by Georgia Marine Extension and Georgia Sea Grant beginning back in 2014. And it's been funded through several different grant cycles by the Georgia Coastal Resources Division, Georgia DNR, where they basically went and digitized and geolocated all of the septic systems in Georgia's coastal counties. This has been just a phenomenal project and a tremendous labor trying to collect and pull together and standardize some widely variable and sometimes difficult to decipher data, and then put it into a modern digital format where it can be integrated with lots of other data sources and used in studies like this. And it's really proven to be a really valuable source of information, and we're really grateful for that work. And so this is some of the output of that. So basically each of these purple dots represents a septic system in Bryan County. And in the graph, you see some data about where those systems, when those systems were installed, and the relative age and the total number you see in the county. One reason we picked Bryan County as the sort of the pilot of this project is because most of its systems have been installed, in the last 30 years. Its population boom in the 1990s through the present has created a somewhat more uniform data set that made it easier to do this type of analysis with. So one of the questions going forward is how we can address some of those data difficulties, even with this valuable data set going forward. But it's proved really useful here and turned out to be a great place to begin. And so we took the data set and all of the records of these septic systems and the data points that it provided as far as system characteristics and whatnot, and we merged that with the county parcel records. And we also zeroed in on the southern part of the county, as you might have seen from the previous slide, or generally being familiar with Bryan County. It is separated. It is cut in half by Fort Stewart, a military installation. And so that made it very difficult to have a uniform data set when we got to some of the hydrogeological, the groundwater data. So we really zeroed in and tried to focus on how to make this work in the southern part of the county. So we merged the septic system data with the parcel data so that we had housing characteristics and some rough demographic characteristics about the people who own the septic system, about the properties on which they were located. And so this is a flow chart about how the project generally worked. Basically, step one was we developed the hydrogeologic framework, which included understanding what the seasonal high water table was, how that related to topography, and then how we could connect the characteristics of that geological setting to septic system vulnerability. And then once we understood the relationship between the groundwater and the likelihood of septic system failure, we then integrated that with different projections of sea level rise, typically at 0.2, 0.5, and 1 meter increments. And then we then looked at the impact of those higher tide levels on the soil moisture and on the soil characteristics that we had associated with system failure, and then generated predictive estimates of how much more vulnerable those systems were likely to be under these future scenarios. So basically, developing the groundwater layer, what we found is there is a pretty uniform groundwater surface throughout the southern part of Bryan County. Basically, the groundwater is the depth of the groundwater is just a function of the topography, that it makes basically a flat sheet that covers the entire study area, which made and then also the relationship of the higher sea level then is almost a one-to-one correspondence. So the higher the sea level goes, you have a corresponding loss of separation between the groundwater and the surface water, which turns out to be very problematic in certain parts of the county for septic system functionality. So to actually understand the relationship between that groundwater layer and septic system functionality, we looked at something called the Soil Topographic Index, or STI. And that is basically a compilation of the site characteristics of the soil texture, the soil type, the topography, based on the DEM and the LIDAR data, and then the depth of the groundwater, and then the soil conductivity, basically how much does how easily is water able to move through that soil, and the STI then being an attempt to have a cumulative understanding of the connection between the increased moisture from a higher groundwater table and the connection that has to the ability of the effluent to percolate in the soil and receive treatment. Some math about how the STI was formed and how it relates to an earlier version of this that looked at how, more basically, how water is able to percolate the soil is called the Topographic Wetness Index, and how we modified that process to create this STI, a novel STI for evaluating these scenarios. So we developed an STI for every 10 by 10 pixel in the county, and you see that it's widely variable across the county. But then we zoomed that out to the parcel level and came up with an aggregate STI score for each parcel. And then we're able to relate that again back to the septic systems that are located on those parcels. And connecting then that STI to the septic records, we identified, of the 3,343 septic systems in the southern part of Bryan County, we identified 1,864 recognized system failures. Basically, we just identified which systems had either a major system repair or a new system installation. As a new system installation being a new system installed that was replacing an old system. Basically, the septic system records either designate things as a repair or a new system. But instead of just counting all of the new system, instead of just looking at the repairs, we also looked at the systems that were identified as new for a parcel that had previously had a recorded system. So basically, where was a new system replacing an old system, we also identified as a failure and a replacement. So again, that's 1,864 identified replacements. And then we looked at the characteristics of the systems that led to those repairs and replacements. And then we were able to identify specific STI criteria that were associated with septic system failure. And then we run it through the sea level rise scenarios and look at how that STI evolves and then how that relates to the septic system vulnerability to that failure. And so here's what we found. Basically, that in the present condition, there are a good many systems that are in the low or moderate risk category. There are a number that are very high risk, and there are a number that just fall into a high risk, an elevated risk. At the very high risk are generally the oldest systems, the ones that were installed before modern, the current sort of phase of septic system regulation that has a mandatory separation requirement for the drain field. These systems are the oldest that predate that, and so they sort of set a particular standard for vulnerability. And that's one of the interesting sidelines of this research, is it really showed how valuable the more recent Department of Public Health standards have been in improving septic system functionality and reducing vulnerability, because those systems, regardless of the sea level rise scenario, still perform better than those systems that have been that were installed prior to those regulations being in place in the mid-1990s. But as we increase the sea level rise, and as we look at these higher level scenarios, you see a shift from the green and the yellow to the orange and the red. And then as a synopsis, you see that a good many, a fairly large shift from those low and moderate categories to that high category, especially when you have, when we start looking at something like a meter of sea level rise, then there are very few systems that are left that are in that low to moderate category. But still, they don't reach that level of vulnerability that you see in those oldest systems. In fact, it is a very minimal increase in those most vulnerable systems. So this was our research team, Dr. Brian Bledsoe and Nahal Hoogie, the College of Engineering, responsible for the STI development and that modeling. And we worked with Dr. Brian Meyer from Georgia State to develop the groundwater data and flesh out that hydrogeological framework discussed. And so, and then we look towards the future and what we're going to do with this research going forward. We look to expand the scope of it. As I said, this was really intended to be a pilot project where we just sort of developed a methodology for assessing this, and then we want to see it expanded at larger scales and across communities where we can do some more comparative analysis. We want to couple it with overland flooding risk and how the increases in precipitation, increases river flooding, and increased tidal flooding will also increase the risk of failure and increase the vulnerability caused by the STI and other such factors. And then we also want to look at how this plays out in other physiographic regions. It was said that the groundwater table, the uniformity and the flatness of the groundwater table in Bryan County really did make this easy in some ways, easier than it could have been. And so we're really curious how it might look in an area with a more variable groundwater setting, more variable subterranean geology and whatnot. And then we also want to consider more about assessing the significance of those treatment failures. If we can come up with a way of understanding sort of the percentage of failure or how to measure the extent of those sort of mid-grade failures where you have something in between complete mechanical failure, but also not a well-functioning system. How can we look at the loss of treatment, of separation distance in treatment capacity? So with that, I thank you again for tuning in to this recording, and I look forward to talking to you at the live sessions. Thank you again.